Okay, so today we're going to look at one of the two of the optimization problems. We're going to start with number 3. So a boat is on the ocean. It's 4 miles from the nearest point on a straight shoreline. So let's kind of get a quick picture of here. So here's my boat. And I'm going to do this in green. The green represents my shoreline. So the distance from the boat to the shoreline is 4 miles. Okay? Then the distance from this point right here to a restaurant on the shore. So let's do that restaurant in purple. Here's the restaurant. That distance is 6 miles. Okay? So, some things that we know. The first thing that we know is that when she rows, and I'm going to call rowing R, when she rows, the rate that she rows at, so dr dt, is 2 miles per hour. And when she walks, so let's see here. Let's get some variables in here before I do that. So let's see if so I do want to get some variables in here, but before I do, so let's kind of think. Before I put in the walking speed or the walking rate, let's look at what's going on here. So what they want to know is where should she kind of park her boat, or where should she row her boat to that would minimize her travel time to the restaurant. So in other words, if this purple line right here, this purple dotted line right here represents her rowing, where along that green line would she have to park her boat, basically, and then walk the rest of the way. So what I'm going to do is I'm going to say, and I will do this in, how about pink? I'm going to say the distance from here, actually, let me highlight that just to make sure you guys see it. So from here to here, I'm going to call that distance x, which means the other distance, the distance from here to here, is going to be 6 minus x. Okay, so what we want to know then, or what they've given us, is they told us her walking speed. That's her change in x. So her change in x, dx dt, is 3 miles per hour. Okay? So the question again is, what should we do to minimize her travel time? So we don't really have anything in terms of time. All we really have, I think you guys would agree, is we have some distances. So I could figure out, I don't want to do that. I could figure out this distance. And I could also figure out this distance. But that doesn't quite help me because I'm not looking for the distance. So what I'm going to do instead is I need a formula that relates distance and time. So hopefully you are thinking distance equals rate times time. That is a formula that relates distance and time, and I can use it to solve for time. So what I'm going to do is I'm going to come up with 2 equations. I'm going to come up with an equation for this, the distance for this, I'll call it d1, and then I will come up with an equation for the distance of the walking. So the distance that she rows, the distance that she walks. Okay? And then I'll solve each of those for time. So let's see we go. Let's start with distance 1. So I think you guys would agree, distance 1 is just a triangle. It's a Pythagorean triangle. So it's going to be, let's see, what is that? It's going to be x squared plus 4 squared. Okay, that's going to represent the first distance. And then the second distance is just going to be 6 minus x, okay? So the first distance is her rowing distance, the second distance is her walking distance. Now, I'm going to have to take each of those and solve them for time. So again, in order to do that, we know that so for the distance one, we know it's distance. So big D, capital, so I'm going to get distance 1 equals the rate of her rowing, which is dr dt times the time that she walks. And I'm going to call that time 1 because I'm going to assume those times are different. Okay? So plugging in some things I know, distance 1 is x squared plus 16. Her rate of change is 2, and her time is time 1. So solving that for t, I think you guys would agree, I get 1/2 the square root of x squared plus 16 equals the amount of time that she rows for. Let's do the same thing for her walking. So in this case, her walking, which is d2, equals her rate of change, which is dx dt times her time. dx dt in this case, whoops. So her distance is 6 minus x. dx dt in this case is 3, and of course that's t2. So we end up with 1/3 the quantity 6 minus x equals that. So next, as I think you guys could agree, the next thing we're going to do is we are going to find her total time. So I'm going to create an equation where I take her total time, which I'm going to call capital T, and that's going to equal time 1 plus time 2. And that is what I'm trying to minimize and maximize. In this case, that is what I'm trying to specifically minimize. So let's see what we got. Let's plug in our stuff here. So time 1 equals 1/2 the square root of x squared plus 16, and time 2 equals, let's see, 1/3 6 minus x. Okay? Got an equation? Let's go take some derivatives here. So, taking the derivative of this with respect to x, what do we get here? So I get 2x over, let's see, sorry, I'm going a little faster myself here. So let's do this a little slower so I don't make a mistake. So I get 1/2 times the derivative of that function, which is going to be 1/2 times 1 over the square root of x squared plus 16 times the derivative of the inner, which is 2x. Okay? Hopefully that is right. I'm pretty sure it is. And taking the derivative of the second function, I get negative 1/3. Okay? So cleaning this up, we get, looks like I get, let me get some canceling out. So I get x over 2 x squared plus 16 minus 1/3. I'm going to get a common denominator for this. So dt dx equals 3x minus 2 square root of 16 plus x squared over 6 square root of 16 plus x squared. Okay, this is the function I need to minimize. minimize. So the denominator I can ignore. The denominator is always positive, so it's the numerator that's important. So let's set that equal to 0. Where am I going to do that? Let's just keep on going, shall we? So I set it equal to 0, so I get 0 equals 3x minus 2 root 16 plus x squared, which leaves me with, how about 2 root 16 plus x squared equals 3x. I'm going to square both sides. So I get 4 times 16 plus x squared equals 9x squared equals 9x squared. So that becomes 64 plus 4x squared equals 9x squared. So 64 equals 5x squared. So x, I'm going to take this and I'm going to do it right here. So x squared equals 64 over 5, which means x equals plus or minus 8. That's a 64, not a 65. Excuse me. 8 over the square root of 5. So that tells us, in terms of where she should kind of park her boat, that she is going to park it, not the negative. She's going to park it, coming back to my picture, so going back to my picture, she's going to park it 8 root 5 from miles from the starting point, so from this point. Okay? So our answer is 8 root 5 miles from the starting point.